Have you ever wondered what a semiconductor PN junction is? It's an intriguing question, isn't it? Now, before we dive into that, let's get familiar with what a semiconductor is. Imagine a world without electronics. Pretty bleak, right? Semiconductors are the unsung heroes that make our electronic lives possible. In the simplest terms, a semiconductor is a material that partially conducts electricity. It's not a full conductor like metals, but it's also not an insulator like wood or rubber. It sits comfortably in the middle, making it the perfect candidate for controlling electrical current, which is paramount in electronics. Semiconductors come in two types, N-type and P-type. The N-type, doped with atoms that have extra electrons, and the P-type, doped with atoms that lack electrons, creating holes. These two work together in harmony to control the flow of electricity. Now that we understand what semiconductors are, let's delve deeper into what a PN junction is. A PN junction, as the name suggests, is a junction between a P-type and N-type semiconductor. So let's dive into the structure of this intriguing junction and get a better understanding of it. The essential building block of a PN junction is the semiconductor, a material that has unique properties lying somewhere between a conductor and an insulator. Semiconductors can be classified into two types based on the impurities added to them, P-type and N-type. The P-type, or positive type, is doped with elements that have one less electron in their outermost shell than the semiconductor, creating holes or positive charge carriers. On the other hand, the N-type, or negative type, is doped with elements that have one extra electron, creating negative charge carriers. Now imagine bringing these two types of semiconductors together. The moment they meet, something fascinating happens. The electrons from the N-type semiconductor start to move towards the P-type, filling in the holes. This movement creates a layer at the junction where there are no charge carriers, known as the depletion region. This region acts as a barrier that prevents further movement of charges, thereby forming a stable PN junction. But we're not done yet. Another crucial characteristic of a PN junction is the built-in electrical field. As the electrons move from the N-type to the P-type semiconductor, they leave behind positively charged ions. Similarly, as the holes in the P-type are filled, they leave behind negatively charged ions. These opposing charges create an electric field that points from the N-type to the P-type semiconductor. This built-in electric field plays a vital role in the functioning of the PN junction, which we will discuss in the next scene. Now that we know what a PN junction is, it's time to understand how it works. So stay tuned as we delve deeper into the world of semiconductors and unravel the mysteries of the PN junction. The working of a PN junction can be best understood in terms of electron movement. To set the stage, imagine a world where tiny particles called electrons are the stars of the show. In the land of semiconductors, we have two types of materials, N-type, where electrons are the majority carriers, and P-type, where holes or the absence of electrons dominate. Now imagine we bring these two materials together. The N-type and P-type semiconductors meet and form what we call a PN junction. Here's where the magic happens. Electrons from the N-type semiconductor start to migrate towards the P-type semiconductor. But why? Well, it's because of a natural tendency towards equilibrium. The N-type has an excess of electrons, while the P-type has a deficiency. So the electrons move from where they are in excess to where they are scarce. As these electrons move across the junction, they leave behind positively charged ions in the N-type region, creating what is known as the depletion region. This region is called so because it is depleted of free charge carriers, meaning there are no free electrons or holes in this area. Simultaneously, as the electrons fill the holes in the P-type region, they create negatively charged ions. This movement of charge carriers results in the formation of an electric field across the junction. Now, this electric field is no ordinary field. It's a one-way street for current flow. The direction of the field is from the N-type to the P-type semiconductor, opposing the initial movement of electrons. This means that once the electric field is formed, no more electrons from the N-type can cross over to the P-type. However, if we apply an external voltage that opposes this electric field, known as forward biasing, we can push electrons from the N-type to the P-type, allowing current to flow. Conversely, if we apply a voltage in the same direction as the field, referred to as reverse biasing, we further prevent electron movement, blocking current flow. So in essence, a PN junction acts like a gatekeeper, allowing current to flow in one direction but not the other. And this, folks, is the fundamental principle behind how a diode, one of the most common electronic components, works. It's fascinating, isn't it? How the simple migration of electrons can give rise to such a powerful concept. That's the beauty of semiconductors. They take us into a world where the tiniest particles have the power to control the flow of electricity, and in doing so, they play a pivotal role in shaping the world of electronics as we know it. This phenomenon is what makes a PN junction work as a diode, allowing current to flow in one direction only. So, where do we see these PN junctions in action? Let's dive in and explore some of the most common applications of PN junctions. One of the most basic applications of a PN junction is in a device called a diode. Diodes are the traffic cops of the electronic world. They control the flow of current, allowing it to move in one direction but not the other. This unidirectional flow is crucial in converting alternating current, or AC, into direct current, or DC. And where do we use this? Well, it's in your phone charger, your laptop power adapter, and many other electronic devices that need a steady supply of direct current. Next up, we have transistors. Transistors are like the brain cells of digital electronics. They use PN junctions to amplify or switch electronic signals. With the ability to turn a small input into a large output, transistors are responsible for the functioning of a wide range of devices. From your smartphone to your digital watch, from your car's navigation system to the space station's communication systems, transistors are everywhere, making our lives easier and more connected. Last but not least, let's talk about solar cells. Solar cells are the heart of solar panels, converting sunlight directly into electricity. And guess what? They're built using PN junctions. When sunlight hits a solar cell, it excites the electrons in the PN junction, causing them to jump from the P side to the N side, thereby generating electric current. So every time you see a solar panel, remember it's the humble PN junction at work, harnessing the power of the sun to bring clean, renewable energy to our homes and cities. So, as you can see, PN junctions are not just theoretical constructs. They are real, tangible, and have a significant impact on our everyday lives. They are in the devices we use to communicate, the systems we use to navigate, and the technology we use to power our world. As we've seen, PN junctions are fundamental to many electronic devices we use daily. From powering our gadgets to providing renewable energy, the applications of PN junctions are as diverse as they are transformative. So, to recap, a PN junction is a boundary or interface between two types of semiconductor material. It's this integral crossroads where the magic of semiconductors truly comes alive. Let's take a quick journey back through our discussion. We began by exploring what semiconductors are. These are materials, remember, that sit comfortably in the middle of the spectrum between conductors and insulators. Their unique property to conduct electricity under certain conditions makes them the perfect candidates for controlling electrical current. Then, we dived into the heart of our topic, the PN junction. This is where a P-type semiconductor, laden with positive charge carriers, meets an N-type semiconductor, teeming with negative charge carriers. The meeting point forms a junction, hence the term PN junction. We delved into the inner workings of this junction, discussing how the movement of electrons and holes across this junction results in the formation of a depletion region. This region acts as a one-way street, allowing current to flow in one direction only. This is the principle of diode, a vital component in electronics. We also explored how this unassuming junction has vast applications. From rectification in power supplies to modulation in communication devices, the humble PN junction plays a pivotal role. It's the backbone of solar cells, converting sunlight into usable electricity. It's the heart of LEDs, turning electrical energy into light. In essence, the PN junction is a marvel of modern science and technology. Its ability to control and manipulate electric current has revolutionized our world, powering everything from our pocket-sized smartphones to mammoth supercomputers. As we conclude, it's worth appreciating the significance of this minuscule component. Its presence may be invisible to the naked eye, but its impact is colossal. The PN junction is a testament to human ingenuity, a symbol of our relentless pursuit to harness the laws of nature for our benefit. Next time you use an electronic device, remember the tiny but mighty PN junction at work.